So we are working on applications of the derivative. In the last video, I introduced a problem to you, and we did part A. We sketched the graph of h of t. Now, it might seem weird that I'm sketching this graph using college algebra information when we're focusing on a calculus applied problem, but I promise a lot of the details that we will be utilizing in part B through F is actually going to come back to that graph. So that's an important thing to keep in mind. Okay, so again, we sketched the graph. It looks like this here. And in part B, we want to figure out how high is the flea after 1/4 of a second. Now, I put in 2 preface questions, which I did cover in the last video, but that was an excellent time to repeat this. When you're doing word applications, it's always wonderful to know what the variables actually stand for. So that helps us interpret the rest of the parts of the problem. So, T tells us is in seconds. So T represents time, and specifically the time in seconds. And what does h of t represent? Well, h of t is our function for sure, but what does that actually mean in terms of this application? H of t talks about the height in meters, how high our flea jumps. So that's what we put here. Our height of the flea jump in meters. Okay, so then when we do the official part B, how high is the flea after 1/4 of a second? We know that our time is going to equal 1/4 of a second, and we're going to figure out height. So basically we just plug in 1/4 for our t, and we're going to get out the height of this equation. So 4.4 times 1/4 minus 4.9 times 1/4 squared. I'm not going to do a whole lot of detail of the math here because we're in calculus now. We don't need to focus on little details like that. So I just typed this in my calculator and it gave me out 79375 behind the decimal here. So if we want this as a height, we should label it, right? How high did it jump? Our height was in meters, 0.79375 meters. And you can round it to whatever you think is appropriate. Now, in the last video, we graphed this, so we can figure out how does this fit back in with that graph. Well, we plugged in 1/4, so 0.25, and we got out 0.75. So that represents this point on our graph right here. So at 1/4 of a second, this is where the flea is at in its jump. Okay, now that we've finished that part, let's move on to part C. And this is where some of the calculus methods that we learned in the last section come into play. Even though this really isn't calculus, this is still college algebra and the calculations here. What is the average velocity of the flea over the first 1/2 seconds of its jump? Meaning between our time equals 0 and our time equals 1/2. So if we want the average velocity, we know we compute that by using the slope formula, and where we need to subtract our 2 y values over our 2 x values. Now we know our 2 x values, or in this example, our 2 t values, so 1/2 and 0. And we know to come up with our 2 y values, we just need to plug both of these points into our equation. So the first thing that we need to figure out is 1/2, and the second thing that we need to figure out is h of 0. Now we actually did h of 0. We did that in the graphing video. We know that comes out to be 0, so I can plug that in for here. And h of 1/2. Let me just plug that into my equation. 4.4 times 1/2 minus 4.9 times 1/2 squared. I plugged that in my calculator and I got out 0.975. So that is what I'm going to plug in to my formula over here. So I really just have to simplify 0.975 divided by 0.5. And my answer is 1.95. So the math is really easy here. This is again still college algebra material, even though we're doing a calculus applied example, because it wanted the average velocity. Okay, the hard part of this then becomes, what do I label it as? I know I get 1.95, but what does that actually mean? Well, if you're ever calculating velocity, which is another way of saying the derivative or the rate of change, or the slope as we said it here, it's going to be something per something. So our label should have actually two labels here, our something per something. And in this case, we want to know what is the rate of its jump. So in this case, it's how high did it jump, our label is in meters, compared to how fast. And so our fast here was in seconds. So over the first 1/2 seconds of the jump, the average velocity of this flea went 1.9 meters per second. Now, if we want to figure out how that relates to our graph, so we plot our 2 points on our graph here. The first one was the origin, and the second one was at 0.5, so that's this right here. So if we wanted to do the average velocity, basically we're computing the slope of the secant line between these 2 points right here. So we want to know what's the average velocity between almost the peak of my graph and my initial starting point of my graph. And we can see that that average velocity was, as we said before, 1.95 meters per second. In Part D, we're going to expand beyond that. We say we don't want to use college algebra material. We want to actually use our calculus methods. So we don't really want the average velocity, although that gives us a great idea to start off with. We want more specifically the instantaneous velocity. And so that's where the derivative comes into play. I'm going to pause this video here, and in the next video, I'm going to come back and I'm going to answer specifically Part D.